Alright, so today we're going to discuss the Indian National Chemistry Olympiad 2004 problems, the problem 7. This problem comes in 5 parts, 7.1 to 7.5, and we'll just directly get to the problem. We'll start with 7.1. Now here, 7.1 says, draw the electron dot structures of the following molecules and highlight the lone pairs wherever they are present. And the first one is HCN. Also identify with the reasoning the most basic species. Alright, we'll do that after. First we'll draw the structures. HCN. So a pretty basic structure. HCN would be this, and the lone pair of nitrogen would be here. So the second is N2H4. Now N2H4 has two nitrogens, so two lone pairs, and the H would be just present over here. So pretty basic structure. CO2 would be like this, and the lone pairs will be present over here. Alright, after CO2 it's CO3 2 minus, so it's the carbonate ion, CO3 2 minus, the C double bond O, and the negative over here, and another negative over here. You can't have two negatives on the oxygen because of obvious reasons. It would like the valency, the octet of this oxygen, of both of these oxygen, is already filled, so they won't accept another negative charge. So we are told to discuss about the most basic species of these. Now here CO3 2 negative is the conjugate base of H2CO3, and CO2 has a lot of lone pairs. Here nitrogen also has a lone pair. Here two nitrogens have lone pair. So the correct answer for most basic is this. Now the reason for this is, if we discuss oxygen first, now oxygen has four lone pairs in the overall structure, and basicity is basically giving its electron. But the problem is, oxygen is more negative than nitrogen. So when you have two elements, say E and F, where wait, so like E and F, where E is say more negative than F, the electronegativity, electronegative than F, the electronegativity of E is more than that of F. So it would try to pull the electron density. That's the tendency of any electronegative element. It tries to pull others and itself's electron density. So it would pull on F's, the electron density that is shared with F element, and it would also pull on its own lone pairs. These electronegative elements don't like to give their own negative charges or their own lone pairs or any electron density. So in a basic attack, what basically happens is, if you have an electrophile, say, and this E is different from this, obviously, this is an electrophile. Any base would try to attack the electrophile with its lone pairs. But here, oxygen is pretty electronegative. Also, it has a hybridization of what, 1, 2, 3, sp2. So it's even more electronegative than regular oxygen, which is like sp3 if possible. So oxygen wouldn't like to be a base. Here nitrogen is sp hybridized, and here nitrogen is sp3 hybridized. Now sp hybridization is more electronegative than sp3 hybridization, and here we have two nitrogens, so these would be preferring a basic attack more than this nitrogen. If you have a electrophile over here, these would prefer to attack the electrophile, because they don't really like, they are electronegative. Nitrogen is electronegative, but they are not as bad or as electronegative as oxygens. So that's the reason why N2H4 would be more basic. And for this SP versus sp3 hybridization, why sp is more electronegative than sp3, that's the more complex reasons. Basically, when you have more percentage s character, I'll just erase some of this. Sorry. When you have more percentage s character, that's proportional to electronegativity. Now there's a whole chart for there's a energy diagram where like sp3 would be here, sp2 would be here, sp would be here, and it's for all elements like c, n, o, f. I'll try to link it in the description, or it will be available on our Discord server. So you can compare the electronegativity of these over an energy profile diagram, and it turns out that the as percentage s between same atoms, when percentage s character increases, the electronegativity also increases, and when electronegativity increases, the atom tends not to give its electron density, whether it's over a bond or it's a basic attack or anything. Moving on, here's the solution, also solution provided in the PPT that will be shared with you. And this is the reason why N2H4 is more basic. Now 7.2, draw the resonance structure of ozone. So ozone has a pretty cool structure. Now this won't be a partial. This will be a full minus charge. Now ozone has there's a negative to pi conjugation in ozone. So this would go here. This would go here, and it would form a resonating structure uh, like this. And what see the thing with resonance is these structures don't really exist. Like we draw a lot of resonating we can you can draw like 15 resonating structures, but that's not what exists in nature. What exists is the resonance hybrid. You usually draw resonance hybrids in square brackets. So this would be the resonance hybrid. These dotted lines represent the electron density movement. So from here, we had the negative charge to negative or electron density to travel over this bond, and this electron density to travel over this bond. So this shows the formation of another bond, or the incoming electron density, and this shows the outgoing electron density. And there would be two there would be a sorry there would be two partial negative charges over both of these oxygens. This would be the resonating structure of ozone, and there would also be a partial positive over here, since this oxygen has three bonds. Sorry, wait. So it would develop a positive charge over here. This shows a delta positive or a partial positive charge over the central oxygen. Whenever we generally with oxygen, generally when you have like three bonds like this, it develops a positive charge because of the valency. Moving on to the next question, this is the answer for 7.2, and this is the resonating hybrid. This here is the resonating hybrid. Now, which of the molecules in 7.1 and 7.2 may be expected to have non-zero dipole moment? Now, in 7.1, 7.2, we had the this resonance hybrid, the ozone, and in 7.1 we had N2H4, which would show a non-zero, right? A non-zero dipole moment. So in these two compounds, both would have non-zero dipole moment, in ozone you can easily see that the electron density, because of the presence of a delta positive here and a delta negative here, and also a delta negative here, the dipole moment would be like this. So since the dipole moment are like these, there would be a net dipole moment in the downwards direction, which is mu. Mu is the net dipole moment. Mu not equal to 0, as well as for N2H4. Now for N2H4 the structure is pretty cool. This is called a hydrazine, and the structure is sort of like this. I'll try to show it to you in a 3D model as well. It's like this, and then there's the lone pair, uh, like this. Now you can see that the lone pair would be having an arrow towards this direction, and this would be having an arrow towards this direction. And since nitrogen is somewhere around 3 or 3.1 in electronegativity, and this is hydrogen is 2.1, there would be a net dipole moment towards nitrogen in this direction. So overall, if you see, the dipole moment doesn't really cancel out. I'll show you the 3D structure as well. So this is the 3D structure of N2H4, sorry, N2H4 hydrazine. It's available on ChemTube 3D. It's a really cool website. You can always check it out. So this is the structure, and the lone pair would be present over the blue spheres are nitrogen, and there would be a lone pair over them. They don't show lone pair in ball and stick models. The lone pair is assumed to be really close to the atom itself, so it's not like a bond. They don't show it separately. It's over the atom. Now moving to the next problem, you can see the solution here. N2H4 in ozone. And okay, so they also wanted us to check the options of 7.1 as well, since HCN is given as an answer. If we go to 7.1, HCN, and the other two are CO2 and CO3. Oh, okay, so we'll discuss these two. First, for CO2, since it's pretty easy, CO2 would have a net dipole moment of 0, because these are like anti-parallel vectors, and both of the sides are the same atom. So it would cancel out. Mu equals 0. For CO3 2 minus, there would be a dipole moment towards this direction, and this, and this. And what happens is, apparently the resultant of these two vectors is equals to this vector. So when you try to like wait, I'll try to draw it on a coordinate plane. That's the doubly bonded oxygens vector, and this is the ionic oxygens vector. The resultant of this vector, the green arrow, is equals to this black arrow, and the horizontal components obviously cancel out, and so the net dipole moment is equals to 0 for CO3 2 minus. For N2H4 we already discussed, and for HCN, now the electronegativity of carbon is more than that of hydrogen, and nitrogen is more than that of carbon, and nitrogen, especially this is also an sp carbon, so it has more electronegativity than a sp3 carbon, and this is also sp nitrogen. It has no more electronegativity, as we discussed earlier, than a sp3 nitrogen. So there would be a net dipole moment in this direction. So mu wouldn't be 0. Okay, so we'll move to the next question. That is So the answer was HCN for 7.3. The answer was HCN, N2H4, and O3. For the next question, 7.4. The electronic structure of N2O may be represented by the following Lewis structures. Which one of the is energetically more favorable? So I'll try to. Okay, give me a second. Okay, so we are given these choices. Now the rule for checking the thermal stability or energetically more stable. The one of the rules is, as I can see a lot of charges, the first thing that comes to my mind is that like charges, I'll just like charges should be far apart, like they shouldn't be near each other. In in this we can see no like charges, and unlike charges should be near to each other. These should be far apart, and these would be near. So that in this I can see that the unlike are near. In this they are near. In this they aren't near. In these two they aren't near. So we are left with two choices. So we are left with two of the options. Now the second rule for checking the energetically stable. So the next thing which we look for when we are comparing the energetically stable is that all the atoms should have their octets filled. Now here in these two, try to zoom in. In these two, we can see all the atoms seems to have their octet filled. Like the nitrogen here has 1, 2, 3, 4, 5, 6, 7, 8. Same with this nitrogen. Like you can count the electrons. Like the in the oxygen, there's 1, 2, 3, 4, 5, 6, 7, and 8. And similar with this 1, 2, 3, 4, 5, 6, 7, and 8. So the valency, the octet is filled for all the atoms, even the central nitrogen. You can count it. Uh, Now the third rule, which would be here applied here, is that the negative charge should be present on the more electronegative atom. Now earlier we discussed that oxygen is more electronegative compared to nitrogen. And in this structure, I don't see any negative charge on oxygen, but here I do see a negative charge on oxygen. And that's why this would be the answer to the question 7.4. Here you can see all the reasoning. Now coming on to 7.5, which is the final question, I assume. Uh, just try to clear it. Yeah. So 7.5 says, using VSEPR theory, calculate the total valence shell electrons in SF4 and SF6. Draw structures with appropriate geometry of these molecules and indicate the locations of lone pairs wherever present. Alright, so for SF4, so whenever you're trying to draw these structures like here SF4 and SF6, when you're trying to draw structures for these, the first thing that I do is write the central atom and then mark the lone pairs. So S would have a lone pair. S is under oxygen, so it has a like O, S, Se, Te, and Po. So S would have three lone pairs like this, and then I just directly attach the fluorines. So just one fluorine, two fluorine, three fluorine, and four fluorine. Now I can it is not the best structure drawn, and neither the correct structure, but this helps me calculate the hybridization. So I have 1, 2, 3, 4, and 5 steric number, which gives me a hybridization of sp3d, which is a seesaw structure. So the actual structure for SF4 is something like this. And this is the lone pair. Now for SF6 we try the same thing. Now S has three lone pairs, and then you just form the fluorine bonds. Sorry, uh, here fluorine, 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 and fluorine. Now this has a steric number of 6, which is sp3d2. That is octahedral structure. We'll try to draw it over here, and this is this hybridization is one of the most common hybridization when you study coordination compounds, and this would be the most common structure, this octahedral structure, which we'll study in coordination compounds. So this is the structure. There are no lone pairs. Okay, I guess you can mark the lone pairs of the fluorines as well. So fluorine would have lone pairs like this, because some questions do trick you like that. I've seen that mainly in JEE, that they'll ask you for the lone pairs, and you always forget the ligand lone pairs, these F lone pairs. So I guess there are a lot of lone pairs in both of the structures. The first structure has 1, 2, okay, so 3 into 4, 12, and 13 lone pairs, and here it has like 3 into 6, so 18 lone pairs. Okay, so these are the structures and these are the lone pairs. What else did the question ask? Draw the structures with appropriate geometry of these molecules and indicate the locations of lone pairs wherever present. Okay, so wherever present does tell you that you should mark the fluorine lone pairs as well. So these are the structures. The structure of SF4 is drawn a bit. It might be a bit difficult to visualize it. Sorry, visualize it 3D. So this should be this bond of F going diagonally. One should be wedge and the other should be dash bond. Like I'll just draw it here. Even I drew it in a bad way. Okay, sorry. So this would be F, F, and then you have a dash bond F and a wedge bond. Sorry, this is the wedge and this is the dash, and this would be the lone pairs with 13 lone pairs in total. So this is the SF4 structure. Now, yeah, I think that's the last slide. Yeah, 13 out of 13 slides done. So this was this problem 7 of INCHO, and okay, so in this question I do feel like I didn't discuss the CO3 2 negative case properly. I'll just add on to it. When we discussed the sorry, I'll just take a few more minutes. When we discussed CO3 2 negative, this was the CO3 2 negative structure for dipole moment. What happens is when you have a structure like this, you see the two negative charges are in conjugation with the pi bond. So these could go in there and it would resonate, and the overall resonating hybrid, as we studied, would be something like this: delta negative, delta negative, and delta negative in square brackets. So you see, the all these bonds are basically the same thing. There's no difference in these bonds. The even the bond order of all these, including the partial charges on the oxygens with the central atom, everything is same. So, and the angle would be, and when you know, in plane and Euclidean geometry you study, when you have a structure like this, and all the lengths and everything is same, like all the three, since all the three ligands or substitutions are same, it would form a 120-degree angle. And when you have vectors arranged like this, alright, it's a vector. So with 120-degree angle, two vectors having 120-degree angle between them of say some magnitude f gives the resultant equals to f. So you have the resultant of these two vectors as f and here f. So these two cancel out. This f and this f cancel out and it gives some mu equals 0. And even for N2H4, uh, N2H4 you can't, it's not easy to visualize it in a 2D structure. When you see the 3D structure, you see the two planes are different for both the nitrogens. So it's not like the vector from this side would cancel out the vector from this side. It's not like they are not directly anti-parallel. They do look like it, but they are not really anti-parallel. The angles are different, or the planes are different, so they don't cancel out. This you get like I don't really remember. It's either 1.8 or something dipole moment, but I could be wrong though. You should really Google that. And Googling should really help you. Like a lot of people think that when you Google, like they would say, "Oh, you're not going to get Google in JEE, but you're not giving JEE or in Olympiad. You're not going to get Google in Olympiad. You're not giving Olympiad right now, or you're not giving JEE right now. Right now, you're trying to practice for it, and Googling is not a bad thing to do. Like even my teachers, when I was preparing, used to suggest me to Google these problems on my own. Like when you Google it, you find 15 more things that are related to your problem, which you wouldn't know if you directly just look for the answer in the back or just think of it on your own. You get to know, okay, so if I Google CO32 minus, I would get to know about its acidic properties, its basic properties, or something new, basically. So that was the problem 7 of INCHO 2004, and this was presented to you by GRAMOLY. If you have any questions, any doubts, you can obviously put them in the comment section. I'll be sure to check them out. Or even better, I would suggest you to join the Discord server. So in the Discord server, it's a more interactive platform. You can directly ask me and other qualified people who are even more qualified than me. You can ask them questions, and or you can even hop into a voice channel and actually discuss your problems over screen share or anything. And it would be much easier process to connect and to interact and ask your doubts or even have non-academic or academic discussions in general. So join the Grammarly Discord server. It's the link is in the description below. And yeah, I guess that's the solution for INCHO 2004 problem 7.